So now what I have is, now you see, in the simple linear model, when beta was a simple number, was a scalar, variance of beta was given an expectation of beta minus beta square. मैट्रिक्स में तो x स्क्वायर नहीं लिखते ना, if x मैट्रिक्स स्क्वायर कैसे करते हैं? x ट्रांसपोज x करते हैं ना, तभी स्क्वायर आता है ना? x transpose x will give you the square, right? So we write this as variance of beta hat is expectation of beta hat minus expectation beta hat transpose beta hat minus expectation beta hat, right? X dash x. Right? This is what? Expectation of, from this I have x dash x inverse transpose. Is it x dash x or x dash?
X dash.
X dash. Is it x dash x or x dash? How do I transpose x? Suppose I have x, okay? See, suppose x is 2 rows, 1 column. So what is it? It has 2 elements. If you square it, there will be cross terms in the 4 cross 4. That can only be obtained by doing x into x dash. 2 rows, 1 column into 1 row, 2 column. It will be 2 cross 2. Right? So this actually has to be this. Alright? Okay? Sure? And this has to be sure? Alright? Okay. Now what is ABC transpose? Suppose A is a matrix, B is a matrix, C is a matrix. What is A into B into C transpose? It is C transpose, B transpose, A transpose. A into B into C, the whole transpose is nothing but C transpose into B transpose into A transpose. C transpose into B transpose into A transpose. Right? So from which I have, so this is then equal to E transpose, X transpose, transpose is X. And what is X dash X inverse transpose? What is X dash X inverse transpose? Yeah? X dash X inverse transpose is simply X dash X inverse, because X dash X was the inverse was a square symmetric matrix. X dash X inverse was a square symmetric matrix. Sure? For a symmetric matrix, what is the transpose of a symmetric matrix? What is the transpose of? How do you define a symmetric matrix? Where the elements of the diagonal, so the second row first column the same as the first row second column. Third row first column the same as the first row third column. So if you transpose such a matrix, what will happen? You will get the same matrix, no? So X dash X inverse को transpose करने से X dash X inverse ही मिलेगा ना? So right, this is right. Sure. Now what is E? What is E into E cross? E into E dash. What is the dimension of E into E transpose? E is an n cross 1, right? So what is E into E transpose? N cross 1 into 1 cross n, which is n cross n. N cross n, right? N into 1 cross n is n cross n, right? And how will it look like? So let's write E. Suppose E is E1, E2, E3, E4, En. And E transpose will be, right? So what will be E cross E into E transpose? First row into the first column will be E1 square. Then E1, E2. E1, E3, E1, En, right? Sure? Right? Sure? And like that? Sure? Yeah? Okay. Now, this is constant, this is constant, this is constant, this is constant. So I can write this as x dash x inverse, x dash, expectation E A dash, right? What is the expectation E A dash? Under assumption of no autocorrelation, no heteroscedasticity, expectation is the expectation of each term, expectation of E dash is the expectation of each term, right? So what will that be? What is the expectation E1 square? Sigma square, because there is no autocorrelation, no heteroscedasticity. Sigma square. What is the expectation E1, E2? 0. So all the odd diagonal elements will be 0 and all the diagonal elements will be sigma square, right? So therefore this matrix will be, so I will get expectation E dash will be sigma square 0, 0, 0, 0, 0 sigma square 0. Sure? Okay? Everybody gets this? If I take sigma square out of this, what I'll get? By this dot sign, there are many lines in between, which I am not writing. Right? So I will get in general sigma square into the identity matrix. Right? Sure? So if there is no autocorrelation, no heteroscedasticity, this quantity can be written as, right? Right? Because this will become sigma square. And I can take sigma square out common. This will then become the identity matrix. So I will have variance of beta hat. Right? Sure? In case of either autocorrelation or heteroscedasticity, this will not be sigma square. This will be some matrix like this, sigma 1 square, sigma 2, whatever. Then general matrix I will call omega. The general matrix I will call omega, and if there is heteroscedasticity then my estimator will become, my variance of beta hat will become x dash x inverse x dash omega right, x dash x inverse x dash omega, then middle term will become omega, some matrix. See, if there is no automation, if there is automation of heteroscedasticity, then not get the sigma square I matrix. Some sigma 1 square, sigma 1, 2, etc. some elements. Let me call that omega. And then that expectation E dash will be replaced by that omega matrix. Right? This is called the hat matrix, the very important point. The hat matrix. Okay? This is called the hat matrix. Okay? And what you have there is called the sandwich. Okay, what you have there is called the sandwich because you have x dash on both sides, and then there is the sigma is the matrix inside, right? So the middle part is called the meat and the southern part is called the bread, right? And the whole part is called the sandwich. It's a very important quantity. Sure? Okay, so if you have autocorrelation of heteroscedasticity, that will be the variance of beta hat for an unknown omega. Right? Then we need to estimate the values of omega to put it there. You have to somehow find the values of omega to get a GLS, right? Whereas if you have no autocorrelation, no heteroscedasticity, then the variance of beta hat will be sigma square x dash x inverse. Variance of beta hat will be sigma square x dash x inverse. Sure? So we'll call it a day today. How much more time do we have? 3. Sure? So thank you very much for listening patiently to me. Right? And I'll please, if somebody can help me, who is free now, who can give me half